So if you think way back when we first started talking about aromatic stuff, we went through all these rules. Is it or is it ain't aromatic? And how do you know if something is aromatic or not? And then we spent so many videos talking about benzene. Benzene can undergo nucleophilic and electrophilic aromatic substitution. Benzene can do so many magical things. Benzene. Well, at the time when we learned about heterocycles, we said a lot of other heterocycles are aromatic. We have not talked about how any of those heterocycles react. It's time to talk about how other heterocycles and things other than benzene that are aromatic react. We've seen pyrrole, furan, and thiophene before. We said all of them are aromatic because all of them have a vinyl, an allylic lone pair, and that allylic lone pair counts toward the aromaticity. So all of those have 6 pi electrons. Remember, when you have 2, only one pair counts toward your aromaticity. Whew, one day. Pyridine is also aromatic because it has 6 pi electrons. That lone pair is vinyl. It does not count toward your aromaticity. So pyrrole, let's draw pyrrole and the resonance of pyrrole just as a pyrrole. Yeah. That nitrogen's lone pair is definitely delocalized. It is part of your pi system. So it can be donated. And we can keep on donating. Round and round and round we go. Well, we can do some more. So if you remember from the kind of worksheet thing we did before, you can draw resonance of benzene and benzene derivatives in order to help you determine whether they are electron-rich or electron-poor. And all of this resonance, in a moment, when I wrap it up, is going to help me to decide if pyrrole is electron-rich or electron-poor. If I drew a hybrid, a resonance hybrid of pyrrole, I would put me a little ... circle all around that thing. I would put a partial positive on the nitrogen because in every single one of those resonances, outside of the first one, we have a positive on the nitrogen. And in every single one of those resonances, one of my 4 carbons has a negative. So all 4 carbons are partial negative. That lone pair on pyrrole 100% donates to that ring, making pyrrole very electron rich or poor. Rich. It's super electron rich. It's got lots of electron density. That nitrogen's lone pair donates all to the ring to make it super electron rich. Because it's so electron rich, do you think pyrrole would be good at electrophilic aromatic substitution or nucleophilic aromatic substitution? Because it's electron rich, it's fantastic at electrophilic aromatic substitution. It's super activated toward electrophilic aromatic substitution. It's so activated that it doesn't require a Lewis acid catalyst. Remember, we saw aniline can add stuff without a Lewis acid catalyst. So can pyrrole. So if we make our electrophile and we just let things go like that, it's not super typical for things to just let go like that and make this acylium, but we're just going to roll with it. And then use benzene's pi electrons to attack said electrophile. Make an electrophile. Yeah. Use benzene's pi electrons. Well, you can use pyrrole's pi electrons to attack said electrophile. And if we add the electrophile to this position, in pyrrole that's called the 2 position, the 2 carbon, our plus would be down there. Or if we added our electrophile to down here, that's called the 3 position, the 3 carbon, there's our plus. We can do resonance of this Wayland-like intermediate, and that lone pair from nitrogen donates, down in this squashy little corner. But the buck stops there. You can't donate electrons from this pi bond toward that positive because that would explode nitrogen's octet. So we got two resonance contributors from the orange, and up here with the purple, pi bond can donate. Plus COO. Ooh, and then lone pair from nitrogen can donate. So the purple gives us 3 resonance pictures of our Wayland-like intermediate. 3 resonance pictures is better than 2 resonance pictures. That leads us to say that parole preferentially reacts at the 2 position rather than the 3 position. Can it react at the 3 position? Yes, but it generally only does so after the 2 position is occupied. I'll explain. Hold on. So then some base somewhere comes to take a hydrogen. We'll do it this way with so many arrows. Yeah, we could have done it from this beginning structure and it been cleaner like that. Either way, we end up with a substitution and our 2 carbon. If we had some sort of intermediate or some sort of reactant where my 2 positions on both sides are occupied with something, then and only then does the 3 position react. But parole preferentially reacts at the 2 position over the 3 position because you get better resonance. Furan also preferentially reacts at the 2 position rather than the 3 position because it's a 5-membered ring heterocycle. So it has the same type of characteristics as parole. So our 2 position will give us more resonance than our 3 position would. So first step is make an electrophile. It's an acylium, just like the last one was. Furan's pi electrons attack the acylium, and we get our Wayland-like intermediate. We could resonate it around, but maybe you're good at resonance by this point. Boy, we have been working on it a lot. Some base, somewhere, comes to take a hydrogen. And we get the 2 substituted product. 5-membered ring heterocycles are electron-rich, super electron-rich. They react rapidly with electrophiles. So all of the big 5 electrophilic aromatic substitution, not a problem whatsoever when you have a 5-membered ring heterocycle. Of those 5-membered ring heterocycles we saw in the beginning, parole, furan, and thiophene, thiophene is the least reactive, the least electron-rich, but it's still very electron-rich, and in fact, more electron-rich than benzene is. So they do electrophilic aromatic substitution quickly, easily. They're good at it. 6-membered ring heterocycles are a different story. If I tried to draw resonance of this pyridine lone pair is not involved in resonance, so I cannot share that anywhere. The only resonance I can do is a pi bond exists between atoms of different electronegativity, so I flip the pi bond, give the electrons to the more electronegative atom. That gives me a nitrogen with 2 lone pairs now, and a carbon with a positive. Is that a great resonance? No, it was way better in the beginning before I started jacking stuff up. That's got a nitrogen with a negative. What am I thinking? That's got a nitrogen with a negative. It was way better before I started jacking things up and just creating charges out of thin air. But I'm trying to prove whether this pyridine is electron-rich or electron-poor. And we see what kind of charge is generated in the carbons, on the carbons. Positives. So a positive on the carbon in your benzene pyridine ring. I'm thinking that seems like pyridine is going to be electron poor. It is electron poor. So there's my 5 resonances of pyridine. The first one and the last one are the winner, chicken dinner, the best. If I drew the hybrid of pyridine, I would draw all my little dots around there. I would put a partial negative on the nitrogen, a partial positive on the ortho, and para spots, but not the metas, because in my resonances, I never had a plus on either of those carbons in any of my resonances. So pyridine and other six-membered ring heterocycles, electron poor. Because it's electron poor, do you suspect it will do electrophilic aromatic substitution? Not well. It's not so good at electrophilic aromatic substitution. That says meh, but it's not legible. It can do nucleophilic aromatic substitution well, because what's good for one is bad for the other, and vice versa. So pyridine is capable of doing electrophilic aromatic substitution, but it's hesitant to do so. We have to cook it to pretty extreme conditions. I meant to say this on the last side and I forgot. This is called the 2-carbon, the 3-carbon, the 4-carbon, and it doesn't matter which side you're on. It's the 2-carbon, the 3-carbon, the 4-carbon. It's not really referred to as ortho-meta-para in heterocycles like this. So if we're going to add an electrophile, do you think we should add that electrophile to the 2-carbon, the 3-carbon, the 4-carbon? Based on our resonance, the 2-carbon and the 4-carbon have positive charges already, and positive next to positive, that's bad. So I'm thinking we should probably add it to the 3-carbon. Well, let's do it with a little mechanism. Make an electrophile. Use benzene/pyridines pi electrons to attack said electrophile. If I did it the purple way and put it on the 3-carbon the way I suspect I should, I would get that Wayland-like intermediate. If I did it the orange way, doing the same arrow, I know. If I did it the orange way, I would put it on the 2-carbon and I would end up with this Wayland-like intermediate. If I draw the resonance of this Wayland-like intermediate, oh, nope, that pi bond does not belong where I put it. Here. Did y'all just see what I did? Oh, man. It's not great. It's not great at all. This nitrogen down here is positive. Do we see nitrogens with positive? Yeah, all the time. But this nitrogen is positive because it has less than an octet. It was involved in this pi bond over here, and I took electrons from it. That is not okay. The nitrogens that we see with positives all the time are nitrogen making 4 bonds. Nitrogen with a positive and less than an octet, unacceptable. That is terrible. Horrible, no good, very bad. Real bad. But the purple version does not ever get me to a terrible, horrible, no good, very bad structure like that. The nitrogen remains as a nitrogen with an octet for my whole Wayland resonance experience. And so as long as that nitrogen keeps an octet, that purple is way better than the orange could ever dream of being. So that's why preferentially pyridine and other 6-membered heterocycles reacts at the 3 position rather than the 2 position. So parole, very, very good at electrophilic aromatic substitution. Pyridine, very hesitant to do electrophilic aromatic substitution, but it can happen if the conditions are right. Because they're electron poor, they react very slowly with electrophiles. It can undergo them, but only under extremely vigorous conditions. It's much better at doing nucleophilic aromatic substitution. You tell me, should this undergo a benzyne or a Mesenheimer intermediate? Should this reaction undergo a benzyne or a Mesenheimer? This is me pausing so that I can put an Ed puzzle question in. Yep, okay. It undergoes a Mesenheimer intermediate. How do I know that? Because we said pyridine is very electron poor, and deactivated benzenes are fantastic for Mesenheimer intermediates. Additionally, this is not a super strong base, and benzene requires that it be a super strong base. This is just a regular old nucleophile. So we add to the carbon that has my leaving group. We get a little OMI there. Minus, this is a Mesenheimer-like intermediate. We'll go ahead and draw the resonance because. Whatever the wonderful wizard was. And we keep on going. And we get to, we get here. This is excellent. What's so excellent about this? If we were to judge these Mesenheimer intermediates, is there any resonance that's any better than any other? That last one is the best. Everybody has an octet in all of them, but carbon with a minus versus carbon with a minus versus nitrogen with minus, nitrogen minus is better. And then that lone pair folds in, and we kick out our leaving group, and we end up with our OMI in place of our halogen. Nucleophilic aromatic substitution through a Mesenheimer intermediate. Pyridine is actually deactivated, so it favors Mesenheimer over benzene. Even if we added a strong base, it would probably do a Mesenheimer instead. While we're on heterocycles, we'll just say that they're actually important in biochemistry and some natural systems. Some amino acids have heterocycles in them. I wish I still remembered all of my 20 essentials, but I don't. Some of them have aromatic heterocycles in them, though. Purines and pyrimidines, we saw that when we first started talking about is it or is it ain't aromatic. That's our DNA bases are based on purine and pyrimidine DNA and RNA bases are based on those heterocycles. Porphyrins are also important in biological, physiological systems. This is a porphyrin. A porphyrin has a ton of conjugated electrons, and because there are a ton of conjugated electrons, it would have a very large lambda max. Large lambda max. And what does a large lambda max really kind of translate to? That means in a UV visible spectrum, it would absorb a high wavelength number, a high wavelength wave. If that wave is in between 400 and 700 nanometers, it's likely that this is a colored compound. Because there's so much conjugation, porphyrins are almost always colored compounds. Like crown ethers, they can chelate metal cations. We have a lot of little lone pairs in the middle of this porphyrin ring, and those lone pairs can chelate metal cations. This lone pair and this lone pair is much better at donating than that lone pair and that lone pair, because the green circle lone pairs are allylic. They are part of the pi system. The red lone pairs are vinyl. They are not part of the pi system. So, yeah, it actually relates to a lot of things. They can chelate metal ions. That's kind of important in things like chlorophyll and hemoglobin and vitamin B12. Hemoglobin chelates iron, and when that iron complexes with oxygen properly, our blood turns red. Chlorophyll is the reason that plants and leaves are green, because chlorophyll has a big porphyrin molecule like this. Vitamin B12, yeah, heterocycles. They're kind of important. They also are what hold all of our cells together, because those aromatic heterocycles can have hydrogen bonding between each other. The pairs that pair, as in C pairing with G, the pairs that pair do so because they have a complementary number of hydrogen bonding sites. This is cytosine and guanine. They have 3 hydrogen bonding sites. They pair perfectly like that. They're aromatic heterocycles. Yeah, aromaticity, kind of important. Maybe you got that by now. Whew, that's a wrap.